Welcome back to Math 104. Suppose that at the shooting range you hit the target with probability 0.7, and that the result of each shot you take is independent of all other shots. You take a total of 6 shots. What is the probability of 2, 3, or 4 hits, where the hits can come in any order? Let's realize that this event that we're being asked about is very similar to what we've just been thinking about. The probability of 2, 3, or 4 hits in any order means, specifically, the probability of 2 hits and 4 misses in any order. Or 3 hits and 3 misses in any order. Or 4 hits and 2 misses in any order. Because we're talking about 6 shots. As you parse the meaning of this phrase, 2 or 3 or 4 hits in any order, don't lose sight of the fact that we are certainly talking about taking 6 shots. That is the experiment. Take 6 shots and see how many of them are hits. In the context of the experiment of taking 6 shots, 2 or 3 or 4 hits means 2 hits and 4 misses, or 3 hits and 3 misses, or 4 hits and 2 misses. Thus far, this problem is just like the sorts of problems we were already thinking about before we introduced unequally likely outcomes. Because of the ors, this event is really a union. Its probability is equal to the probability of 2 hits and 4 misses, plus the probability of 3 hits and 3 misses, plus the probability of 4 hits and 2 misses. In each case, this means in whatever order, not in one specific order. Of these 3 simpler events that we've boiled the problem down to, we've already found 2 of the probabilities. We've already figured out that the probability of 2 hits and 4 misses in one particular order equals 0.7 squared times 0.3 to the 4th, which I've written out in gory detail here. But there are 6 choose 2 copies of this number that have to be added up to get the probability of 2 hits and 4 misses in any order. Now we can do the same thing for 3 hits and 3 misses in any order. In one particular order, there is a 0.7 to the 3rd times 0.3 to the 3rd probability, and therefore in any possible order, there are 6 choose 3 copies of this number. Added up, those give you the total probability of 3 heads and 3 misses in any order. Similarly, we have found that for 4 hits and 2 misses, there are 6 choose 4 copies of 0.7 to the 4th times 0.3 squared. Each specific outcome with 4 hits and 2 misses contributes 0.7 to the 4th times 0.3 squared, and we add up 6 choose 4 copies of them. Just to clean this up a bit, let's write 6 choose 2 as its actual numerical value, 15. So that's row 6, entry number 2 in Pascal's triangle times 0.7 squared times 0.3 to the 4th, plus 6 choose 3 equals 20, the middle entry in row 6 of Pascal's triangle, times 0.7 cubed times 0.3 cubed, plus the other 15 in row 6 of Pascal's triangle, that 15 times 0.7 to the 4th times 0.3 squared. I wrote these out in gory detail just to remind you of what they really mean. When you're first learning this, it can be easy to forget what the thought process was that led to them. When you compute this, it turns out to be approximately equal to 0.5689. Now that we've worked through some examples, we'd like to identify what the pattern is, and in particular, we'd like to end up with a formula. A formula that inputs the number of shots, the number of hits that we're interested in, and the probability of a hit on each individual shot. We'd like a formula that takes that information as an input and can tell us the probability of the event we're looking for as an output. Let's work our way step by step towards such a formula. Let's think if you take n independent shots at the target. Not necessarily 6 as in the last example, but n independent shots. What is the probability of 2 hits followed by n minus 2 misses in that specific order? It is a product of as many copies of 0.7 as there are hits, namely 2, times the product of as many copies of 0.3 as there are misses, namely n minus 2. That's it. That's all we need to write and all we should write, because we are asked about 2 hits followed by n minus 2 misses in that specific order. But now, if you take n independent shots at the target, what is the probability of 2 hits and n minus 2 misses in any order? Now we've got our n choose 2 to count how many outcomes there are with this probability 0.7 squared times 0.3 to the n minus 2. Each individual outcome contributes 0.7 squared times 0.3 to the n minus 2, but we have to add up a bunch of copies of this number, as many copies as there are outcomes in this event. In other words, as many copies of this number as there are n letter words with 2 h's and all the rest m's. Let's take it a step further. If you take n independent shots at the target, what is the probability of k hits? Not necessarily 2, but k hits, followed by all the rest misses, in that specific order. Please don't be intimidated by the fact that now we're working mostly with letters and hardly at all with numbers. Each letter is simply taking the place of a number we've been working with. So we're working in one specific order. We have 0.7 raised to the number of hits. We have a product of as many copies of 0.7 as there are hits, times as many copies of 0.3 as there are misses, and that now is n minus k. Probability of a hit raised to the number of hits times probability of a miss raised to the number of misses. That's for one specific order. You can sense what's about to happen next. If you take n independent shots at the target, what is the probability of k hits and n minus k misses in any order? That is now n choose k. N choose k times 0.7 to the k, 0.3 to the n minus k. If you believe the answer to the previous question, that this number right here really is the probability of k hits and n minus k misses in one specific order, then to find the probability of k hits and n minus k misses in any order, we have to add up as many copies of this number boxed in red here as there are different possible orderings of k h's and n minus k m's in a word with that many total letters. And n choose k is exactly the entry of Pascal's triangle which counts that number of words. So number of shots taken, choose number of hits, is exactly the right entry from Pascal's triangle to count how many copies of this number in red need to be added up to find the probability of k hits and n minus k misses in any order. If you believe that, now suppose that the probability of a hit on each shot is p, not necessarily 0.7, but we're just going to call it by a lowercase p, so that the probability of a miss on each shot must therefore be 1 minus p. If you take n independent shots at the target, what is the probability of k hits followed by n minus k misses in that specific order? Instead of 0.7, we have little p raised to the number of hits times 1 minus p instead of 0.3 raised to the number of misses. Right? If you have hit, k times, followed by miss, n minus k times, for each hit there's a p, and we have a certain number of them multiplied together, and for each miss there's a 1 minus p, and we have a certain number of them multiplied together. This is for just one specific order of the k hits and all the rest misses. If you take n independent shots at the target, what is the probability of k hits and n minus k misses in any order? Think for a moment what this should be. It should be the answer to our previous question multiplied by how many such outcomes there are, and that is n choose k outcomes that are of this form, with k hits and all the rest misses. Wow, we've worked our way to a formula that has all letters and no specific numbers. This is actually good news. Congratulations! We have just reasoned out what is called the binomial probability model. If you take n independent shots at a target, with probability p on each shot of hitting the target, then the probability of exactly k hits in those n shots equals n choose k times p to the kth power times 1 minus p to the n minus k power. And to make this an even more explicit formula, we can take the n choose k here and just write what it equals in terms of n's and k's and factorials. That may look a bit intimidating, but there are many examples, and with practice this will become entirely natural. Speaking of practice, before going on to the next video, find the probability that on 10 independent shots at the target, with a 60% probability of a hit on each individual shot, you hit the target exactly 6 times. And for reference, here is the formula.